Hello, this is Philip Myers of PEMY Consulting. Welcome to Unit 4, the Math of Units. In order to be comfortable with working with engineering units, you have to know a few basic unit combinations. For example, you already know that area is the dimension of length squared, or that acceleration is length per time squared. We have density, mass per volume, or length cubed. In SI, it's kilograms per cubic meter, or in USCS, pounds mass per cubic foot. We have the Newton, the moment, and work or energy. We won't go over those since we previously covered those. The rate of work is power. That's force times length divided by time, or Newton meter per second. In USCS, it would be foot-pounds of force per second. So 1 watt is 1 joule per second. It's 1 Newton meter per second. 1 horsepower is 55 feet-pounds per second. Pressure is force per length squared. It works out to newtons per square meter, or the Pascal. Here are some exercises that you should be able to easily do. So what's wrong with or right with these statements? Well, this one is clearly wrong because you cannot have different kinds of units added together. This one looks correct because 1.5 times 3 is 4.5, and we have feet-pounds force, or foot-pounds force. So this one's okay. This one you can take a square root of units provided that they work out to something reasonable. So we'd take the square root of 4, which is 2, the square root of feet, which is feet squared, which is feet, and the square root of seconds to the minus 2, which would be seconds. So although it's written this way, you should do the actual documentation of the conversion factor, 12 inch per foot. These cancel, and you're left with 24 inch per second. Note that there is an error here, so this is incorrect. This particular statement is fine. If you cross out the pounds force, you end up with adding grams. So 4540 after multiplying by 10 plus 5, 45 grams would be the total of this statement. Although this appears to be correct numerically and unit-wise, there is no unit called the foot-pounds mass. There's a foot-pound force, but not the mass. So probably here what was meant was this, foot-pounds mass. Dimensional consistency and homogeneity. These are fancy words for a very simple concept. The units on both sides of the equation must match exactly. Homogeneity, every additive term in an expression must be exactly the same. You cannot add apples to oranges. So here are some examples of correct and incorrect statements. Here you can see that 5 square feet plus 3 square feet plus 288 square inches. This has to be converted to square feet. So 288 divided by the 144 square inches per foot gives you 2 square feet. So this is fine here. Read this little note to familiarize yourself with the concept of arithmetic and on units. Here is a real example of an engineer's calculations, one who I supervise, and here is his computation of the hydrostatic head, or the pressure caused by a certain 47.75 feet of liquid of specific gravity 1.0. Although the calculation is not incorrect, there are some improvements that should be noted. First of all, big G is reserved for Newton's universal gravitational law. Little g is reserved for Earth's gravitational constant, so that should be a little g. You want to stick with convention so you don't confuse people. He used slugs, which is okay, but it's not something that we use in our company, so that just came from some school training randomly. He also did not label pounds. Pounds mass, pounds force. That should always be done so that it makes it easier for checking and on the reader to understand exactly what is being done. Another improvement is to use pressure is equal to gamma H instead of rho G H. Why? You'll see in a second in this example down here. Also, he used 32.174 here and 32.17405 here. That's puzzling because you wouldn't expect to have higher accuracy in one number or the other unless there was some good reason. So it implies things that aren't there. They should be the same length of decimals. So in this example done in this improved way, you could take P is equal to rho GH. You have rho, pounds 62.43 pounds mass per cubic foot. And then G is 32.2 feet per second squared. Now we have to divide by our conversion factor to get rid of the pounds mass here so that we end up with pounds force per square foot. And if you do this multiplication and conversion from feet to square inches, you get 20.7 psi. Now I like to use specific weight, gamma, instead of rho g because it just eliminates one step. So this is directly, gamma is directly pounds force per cubic foot. It's converted already, so gamma is equal to rho g. And you can see this calculation is much simpler and cleaner. Here we'll take a simple example of converting density from SI to USCS. If you're given these, you can look these up on the internet, the conversion from pounds mass per kilogram, or 3.281 feet per meter. Then you could take water, which has a density of 1,000 kilograms per cubic meter, multiply it by a conversion for pounds from kilograms, or 2.2 pounds mass per kilogram. The kilograms will cancel out, and then you divide by 3.281 feet per meter, but you have to cube this because meters is in cubes. When you do that, you end up with 62.43 pounds mass per cubic foot. Now an easier way would be to look it up on the internet. Here you can see that by typing in 1,000 kilograms per cubic meter, you end up with 62.43 pounds per cubic foot. This is better to do to save time, but you should be able to do this just to check yourself to make sure that you're capable of converting units like this. Very simple conversions. Here's another conversion of pressure from SI to USCS. We're given the same two conversion factors. So what we want to do is convert pressure, which is newtons per square meter. Its dimensions are force per length squared. We know that a newton is a kilogram meter per second squared. We have to divide it by the meters squared here. If you cancel out the meters, you get kilogram per second squared meter. Now we need to convert kilograms to pounds mass with this factor that was given up here, and then convert the meters to feet with this factor. So in order to know whether you're using these conversions in the top or the bottom, you have to just make sure the units cancel out appropriately. So for example, we want pounds mass on the top and we want feet on the bottom. When you do the calculations, we end up with 0.6721 pounds mass per second squared per foot. But pound mass is not the right unit. We want force per length squared. So we have to take our conversion factor of 32.2 foot-pounds mass per pound force second squared. And when you do that cancellation of units, you'll end up with 0.672 divided by 32.2, and then the units of pounds force per square foot. This is what we want. It turns out to be 0.021 PSF. Again, after having done this once or twice, you can just look these things up on the internet. 1 Pascal is 0.021 PSF. Here we're going to convert static head to pressure. If you were to take a column of liquid 23 meters high and put a pressure gauge on the bottom, you would have pressure here. So how do we do that? Well, P is gamma or rho GH or gamma H. We'll do the rho GH form of pressure. We take the 1,000, presuming it's water, kilograms per cubic meter. The gravitational constant in the SI system is 9.81 meters per second squared times 23 meters. Multiplying that out, you get 225,630 pascals. A Newton per meter is a very small unit because the unit area is a square meter. It's much bigger than a square foot. So often we'll just take this, divide it by 1,000, and call it 225.63 kilopascals. Now here we're going to convert dynamic to static pressure. We'll learn more about that in the next module, but you'll recall from school that potential or kinetic energy is 1/2 mv squared. Well, this is 1/2 rho v squared. So instead of m, you have mass per unit volume. The units are kilograms per cubic meter times meters squared per second squared. If you simplify the units, we end up with kilogram meter per second squared. That's a Newton, and then divided by meters squared. So we have newtons per square meter or pascals. Note that when you do these conversions, you want to carry along any constant so that you don't forget about them later. If rho is 1,000 kilograms per cubic meter and V is 18 meters per second, what is the pressure energy in SI and USCS units? Well, we take the 1/2 rho V squared, so 1,000 times 18. This has to be squared, so the units get squared. And we end up with newtons per square meter, 162,000 pascals, or 162 kPa. Here we're going to convert to USCS units, so we just use the 2.2 conversion factor and the 3.28 feet per meter conversion factor. Multiplying it out, we get 108,658.5 pounds mass foot second squared. But note that this is pounds mass, and we don't want that. We know that we're talking about pressure, so that has to be pounds force. Again, we have to divide by the conversion between pounds force and pounds mass. When you do that, you get 3374.5 pounds force per square foot. Summary. What have we learned? Well, with water, we computed a density of 62.43 pounds mass per cubic foot. I usually just use 62.4, and that's generally close enough for the engineering answers that are needed. 1 Pascal is 0.021 PSF. This is not necessary to remember, but we're going to use these values in the next module. 23 meters worked out to 225 kilopascals. And then if you have water moving at 18 meters per second, the pressure that's represented by that moving kinetic energy is 3374.5 PSF. Next time we will talk about Bernoulli's flow equation. Thank you.